All right, today we're going to dive into a really fundamental property of matter, one that basically decides how electricity moves through, well, everything. It's called electrical resistivity, and it's the secret sauce behind why some things give you a zap and others don't.
So let's kick things off with a simple question you've probably seen a million times, but maybe never really thought about. Why is your power cord built like this? You've got that shiny copper on the inside and this flexible, rubbery stuff on the outside. The answer is at the very heart of what we're unpacking today.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, so we all kind of get the basic idea of resistance, right? Some materials are like superhighways for electricity, and others are more like a brick wall. That opposition, that difficulty for electricity to flow through something, that's what we call resistance.
But here's the thing, an object's resistance isn't just one simple property. It's actually the result of a few different factors all working together. You've got how long the wire is, how thick it is, and this is the big one, what kind of stuff it's actually made from.
You know, the easiest way to wrap your head around this is the classic water pipe analogy. Just picture it. Trying to force water through a super long, skinny garden hose is a lot harder than pushing it through a short, wide fire hose, right? It just takes way more effort. Well, electricity behaves in a surprisingly similar way. Okay, and this slide right here, this gets to the absolute heart of the matter. Resistance belongs to an object, like that specific 2-foot-long copper wire on your desk. But resistivity, that's a property of the material itself. It's the copperness of copper. It's the fundamental quality that tells you how much the stuff fights electricity, no matter its shape or size. So if length and thickness are about an object's shape, let's zero in on that third most important factor, the material itself. This brings us right to the core concept of resistivity. So what is it exactly? Well, resistivity, which we represent with the Greek letter rho, is an intrinsic property. That just means it's a baked-in part of a material's identity, just like its color or how dense it is. It's a pure measurement of how much that substance naturally fights against the flow of electricity. Now, here's the more textbook way of putting it, but what does that actually mean? Well, just imagine you could take any material and carve it into a perfect little cube, 1 meter by 1 meter by 1 meter. If you measured the resistance from one face to the opposite face, that number you get is its resistivity. It's how we get a standard apples-to-apples comparison. And of course, because this is science, it's got to have a unit. We measure resistivity in something called the ohm meter. This lets us put a real hard number on a material's electrical personality so we can compare them all directly.
All right, so we've nailed down that resistivity is all about the stuff something's made of. Now let's circle back and see exactly how the physical shape of an object, its geometry, changes its total overall resistance.
And honestly, this is pretty intuitive when you think about it. First, the longer the wire, the longer the journey for those little electrons. They've got more stuff to bump into, which slows them down. So more length equals more resistance. Simple. And second, a wider area is like adding more lanes to a highway. More traffic can get through at once, so a bigger area actually decreases the total resistance. Okay, so we have all the key ingredients now, right? We've got the material's built-in resistivity, the object's length, and its thickness or area. Now we can put it all together into one simple, really powerful formula. Everything starts with the material's fundamental property. The baseline, the starting point for the resistance, comes directly from that resistivity number, our friend rho. Next up, we have to account for the journey those electrons have to take. So we multiply by the length, because like we said, a longer path means more of a struggle, more total resistance. And finally, we factor in the width of the path. We divide by the cross-sectional area, which is just a fancy way of saying how thick the wire is. A bigger, wider path makes it easier for the current to flow, so it reduces the total resistance. And there it is, voila! Resistance equals resistivity times length, all divided by area. This elegant little equation is a huge deal. It's used by engineers every single day to design everything from the tiny circuits in your phone to the massive power lines that crisscross the country. So now we can see why choosing the right material is so absolutely critical. By picking materials with wildly different resistivity values, we can either make electricity flow like a river or stop it dead in its tracks. I mean, just look at these numbers. They are wild. On one end, you've got copper with a resistivity so tiny it has 7 zeros after the decimal point. It practically begs for electricity to flow through it.
Now, look at glass or Teflon. Their resistivity numbers are astronomical. A 1 followed by 12 or even 24 zeros. They fight electricity with everything they've got.
This chart really tries to drive home the sheer scale of the difference. And honestly, it's not even drawn to scale. If it were, the bar for copper will be so small you couldn't see it, while the bar for glass would be millions of miles high. It just shows you they're not even in the same universe.
And this brings us right back home to our original question. The power cord uses copper on the inside precisely because its resistivity is practically zero. It lets electricity flow super efficiently. And it's wrapped in rubber or plastic because their resistivity is so incredibly high that it keeps all that electricity safely contained inside the wire, and not in you.
So, let's do a super quick recap. If you remember anything, remember this. Resistance is for a specific object with its shape and size. Resistivity is for the raw material. Got a low resistivity? You've got a conductor. Got a high one? You've got an insulator. It really is as simple as that.
And that leaves us with one last pretty cool question to chew on. We've seen materials with incredibly low resistivity and insanely high resistivity. But what if? What if a material had zero resistivity? Absolutely none. What could we build with a perfect conductor? It sounds like science fiction, but it's the real world of superconductors, and that opens up a whole new world of amazing possibilities. Something to think about.
Thanks for watching.